As a matter of fact, our substantive discussion will focus on experimental approaches to superconductivity. We will discuss the Meissner Effect explanations of today's topic. This is an interesting topic to discuss. When a superconductor is cooled in a magnetic field below the transition temperature, Meissner discovered that the line of the induction B are pushed out at the transition. Here is a graph you might find interesting things. As a result of the Meissner effect, bulk superconductor behave as if they are the inside in a specimen B equal to 0. A particularly useful form it is the result that can be obtained if you have limit ourselves to long thin specimens parallel to BA. As we know, B is a line of the induction, BA is a applied magnetic field, the capital M is about the magnetization. So therefore B is no longer be demagnetized by the demagnetized field. Therefore the equation B equal to BA plus mu naught M, so that B equal to 0. Here the diamagnetic materials are highlighted or marked in the way to indicate that they became a diamagnetic. So the diamagnetic is a poor magnetization in opposite direction. Here Bm lesser than B naught. So chi m value small negligible or negative and comparing the temperature independent. So that chi m directly proportional to T naught. So that superconductivity has its essential properties of perfect diamagnetism according to the Meissner effect. The difference between a superconductor and a perfect conductor goes further than just its conductivity. So, an infinite mean free path is provided by the electrons in a conductor. Problems are solved in details when they are solved. A perfect conductor cannot produce a permanent eddy current when placed in a magnetic field. Accordingly, about 1 centimeter will be penetrated in an hour by the field. So typical examples, it's a bullet train. As an examples of M magnetic curve, magnetization curve for a superconductor under the conditions of the Meissner experiments can be seen in a figure 4a. Figure 4a talking about to the magnetization y-axis versus applied magnetic field and x-axis for a bulk superconducting exhibit is a complete Meissner effect is called the perfect diamagnetism. Yeah, superconductor, which is a big wave, is called the type 1 superconductor. Above the critical field, the basements of a normal conductor and the magnetization is too small to be into the scales. So therefore, noting that the minus 4 pi m is plotted to the vertical scale and the negative value of the m corresponding to the diamagnetism. So what we understand from the graph 4a, the type 1 semiconductor, the type 1 superconductor is a perfect diamagnetism. So type 1 semiconductor is called the superconductor. In addition, look at the graph is the superconductor T lesser than Tc, so which means the resistivity equal to 0. A long magnetic field can be applied quantitately to the specimen in the form of a solid cylinder. As a result, many materials are exhibiting the behavior reference to the type 1 semiconductors. So as we know, the type 1 semiconductor is simply about formally soft superconductors. Generally, the value of the HC into the superconductor, as you know, the HC value means is a critical field, is a two value of the technical into the coil. So the superconductor is into the purposes. So this type of materials are known as a type 2 superconductor because of the magnetization curve is similar to that of the figure 4b. Look at the graph in the figure 4b. In the particular case, the figure 4b is about the type 2 semiconductor. Type 2 semiconductor is nothing about the hot superconductor. So which means the hot superconductor is a type 2 semiconductor. The flux starts to the penetrating the pavement of the field HC1 into the lower and to the and the superconducting electrical properties up to the C2. So here is the C1 is talking about superconductor states and the C2 it's talking about to the normal states. In the between the electrical field is talking about to the vertex states. So the vertex states, which means why the specimen's vertex is between the HC1 and HC2 conductor is every respect respecting to the possible surface defects. So that the above the HCs are under the magnetization curve in the same of the type 2 semiconductors. As you can see in the figure 5a, Type 2 superconductor strengths, alloys and transition metals which have a high value of the electrical resistivity in the normal states. Before to understand to the normal stage, then the previous discussions we discussed about the normal state into the upper right. Look at the graph. The normal state into the upper right and the superconducting state into the lower state. So now we can understand that type 2 semiconductor is a odd superconductor, which trends is alloys and transition metals. So the alloys and transition metals have a high value of electrical resistivity in the normal state into the upper right. So which means the normal state electrons have a short mean pre-fourth. Right. Laterally we will see why superconductor are magnetized by the mean pre-fourth. Based on this, we can see the type 2 semiconductors have a superconducting properties up to the field of the Hc2. Already we know what is the mean by the Hc1 and Hc2. Between the low critical temperature from the graph, the low critical temperature of the Hc1 and the upper critical field Hc2, the completely the line. Look at the line is dotted lines or disconnected continue lines. Dotted lines completely through continue lines, which means the flux density B not equal to 0 and the Meissner effect is said to be incomplete. Because the H2 value may be is the 100 times or more than the figure 5b at the value of the critical field, and the HC because of the lines is disconnect lines and the continue lines in a single critical field is calculated from the reason about the thermodynamic of the transition. Anyhow, in the region in the Hc1 and Hc2, the superconductor threatened by the flux lines and is said to be the vertex region. We are dealing with the cases with a hot superconductor produces a high steady field over 100 kilo gases likely commercial solenoids. As we can see the graph, the solenoid magnetic field equations, the magnetic field equations is nothing about B is equal to mu Ln. As you know, the B is a magnetic field inside the coil, inside the solenoid, and the mu is about the permeability of the medium, and N is the number of turns per unit length, and I is current. As we know the very easily that type 2 semiconductor is nothing about the hot superconductors. The examples of the hot superconductor with a large magnetic hot superconductor means alloys or transition materials have a large magnetic hysteresis loops. So what does it mean exactly the hysteresis loops from the particular graph? In the hysteresis loop is the showing the relations between the from A to A, B, C, D and until F. The relationship between the magnetic flux density and the magnetic field strength. I would repeat again, the hysteresis loop relations between the magnetic field strength and the magnetic flux density and the magnetic field strength. The loop is generated from until A to F by measuring the magnetic flux coming out from the ferromagnetic substances while changing the external magnetic field. So the relations between the magnetic flux density and the magnetic flux strength is based on the ferromagnetic substances. So such substances means here, just I would like to here the repeat the such substances means here is a ferromagnetic substance have their important application, medical applications in terms of the MRI scanning is called the magnetic resonance images. So look at the graph here. I don't want to go too deeply into the particular graph, but in our cases we are talking about the type 2 superconductor is a odd superconductor. So in that case, odd superconductor materials is a form of a ferromagnetic materials like alloy or transition materials, which means the alloy and transition materials have a higher resistance value into the normal state. During this presentation, remember the following points. We have the 5 following points here. The type 1 semiconductor, the type 1 superconductor is a soft superconductor. Type 2 superconductor is a hot superconductor. And the point 3 is the relations between the superconductor and the perfect conductor. Superconductor and the perfect conductor is nothing but the electrons in a conductor. The fourth point is talking about the thermodynamics of the transition. Why we are studying about talking about the thermodynamics of transition is critical field HC. Just I want to recall that the critical field means in the previous before slide we talk about the disconnected line to the connected continuity line. So the final one is about the vertex state. The vertex state is HC1 to HC2 HC2. So HC1 we are talking about the superconducting states. Superconducting state is talking about the flux, and HC already we know the critical field, and HC2 in the state of the normal state, about the electrical field properties. So those 5 points is our takeaway message. So in final, what is meant by Meissner effect, or the definition of Meissner effect is a cooling materials below a critical temperature brings about the Meissner effect, which is an interesting phenomena. So a magnetic field is a completely ejected from the interior of a material, alternating its magnetic properties. Therefore, many technological advances have been made possible thanks to the Meissner effect in superconductivity. As a result, I hope that we were able to gain a deep understanding the Meissner effect. However, I would like to thank you for watching the video, for sharing it, and for subscribing to my channel. In order to improve our next video, I would greatly appreciate your comments and feedback. In the next video, we will continue to discuss about the heat capacity. Until goodbye.